I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on electromagnetic waves, wavefronts, diffraction, and visible light waves. In this video, we're going to be talking about electromagnetic waves, wavefronts, diffraction, and visible light. So let's talk about light as a wave. So light is a form of energy that travels as an electromagnetic wave. Unlike other wave types, light does not need a medium to travel through, and light waves are slower when the medium is more dense. We're going to start by talking about wavefronts. And a wavefront is added to a ray diagram. So we draw a ray of light. And what the wavefronts represent is the wavelength of that light. So what we're drawing is the crests of that wave. So the distance between those lines represents the wavelength of light. Now, if we draw wavefronts with reflection, we're first going to draw our incident ray on the mirror, and then we're going to add our wavefronts to show the wavelength of light. And we draw our second ray, knowing that the reflected ray is equal to the incident ray. And because there's no medium change, we know that the wavelength is not going to change. So we end up with the same wavelength as we had heading towards the mirror. Now, if we talk about refraction, where the wave of light changes medium, going from air into water, we draw an incident ray at that boundary. We'll draw our wavefronts to represent the wavelength of light. Then we'll draw the normal line to that surface between air and water. And we know that when light travels from a less dense medium, as air, into water, that the ray of light bends towards the normal. It ends up with a smaller angle in relationship to the normal. So let's look at our equation for wavelength. What we know for light is that when it goes into a more dense medium, the speed changes. The frequency of light is just the color of light. We know that the color doesn't change when it goes from one medium to another. So that means the wavelength is what's going to have to change. So if the wavelength changes and speed changes, we know those are going to be a direct relationship. So slower speed means shorter wavelength, so our wavefronts would be drawn closer together. Now we're going to talk about diffraction. And diffraction is the spreading out of a wave as it moves around an obstacle or passes through an opening. So this is why you can hear somebody talking if they're standing around the corners, because the sound wave bends around that corner. Now it occurs best when the opening is about the same size as the wavelength of the wave, and a wave spreads out more as the opening is decreased. Diffraction occurs with all wave types. A couple of examples: sound, light, and water waves. First, we're going to talk about sound. So diffraction with sound, if we send a sound wave towards an opening, what's going to happen is as that wave passes through, it bends and it spreads out. So that's why you're able to hear around corners. Now, if we decrease the size of the opening, what happens as that wave goes through is it spreads out more, covering more area. So you can see the wave is spread out a little bit more on the right side of that opening. Now here's a simulation that shows as the wave is passing through a larger opening, the wave does not spread out as much as it does when the opening is smaller. So we're going to look at diffraction of light. Now, if light were not to diffract, when we had two openings like we see on the screen, and we sent a laser beam towards those two openings, what we would expect to see is that light would just pass through those openings, and we would see that the two openings would produce just two dots on the screen. Now, Thomas Young performed this experiment, but that is not what happened when that experiment was performed. Now, the slits, the way they're set up is the opening is about the same width as the wavelength of light, and those slits are very, very close together as well. Now, what happens when the light passes through there is that we end up having the diffraction of light, and it spreads out as we saw with the sound waves. Now, remember that the arcs represent the crest of the wave, and halfway in between would represent the troughs. So where crests line up, you'd have a larger amplitude, which means you'd have brighter light, and where crests and troughs line up, you'd end up with no light at all because it completely cancels out. Now, what Thomas Young found is that you had a bright spot right across from the center of the two slits, not right across from one of the slits, but in the middle, and there were other dots that appeared as well, and it showed that they got dimmer as they went further and further out. Now, the reason this occurs is if we look at the way that our crests are lining up, we draw a line and we can see that the crests are all lined up straight along that line, which means that we end up with a larger amplitude of light at the screen, which means that it is brighter. And then we can do that for the next two pairs of dots. And then the next two, we can see that we just ran out of screen for that bottom portion, but we'd end up with another dot. And as long if we kept going further and further out, eventually we'd run out of space that we wouldn't have the light spreading out enough, but we'd at least get to these zeroth order, which is the middle, the first order bright magnitude, and then the second order is what we're going to look at. And you can get to a third order if the screen was large enough, but it's going to be pretty dim. Now you can also see that where a crest and a trough line up, that's going to cancel out the light. So halfway in between the bright dots, you're going to end up with no light at all. It's going to be a dark spot on the screen, so you're not going to see anything. So if we shine light through these openings, what you would see is the bright gets dimmer and then it gets completely dark, then it gets brighter, but it doesn't reach that same brightness as n equals 0 spot, or the 0 order magnitude. And then you have the first order and second order beyond that. Now, what happens is the waves reach the screen and they're in phase when they reach the screen when it causes a bright spot, and that's constructive interference that is occurring. And you can see that in this simulation where the light passes through and you have the bright areas, the orange areas where the red arrows are pointing to, that's where you have constructive interference. Now, on top of the constructive interference, in between, you have sections on the screen where the waves are out of phase. We have destructive interference. We see the crests and troughs line up, and that's where the dark spots are appearing on that screen. So now looking at Young's double slit experiment, so we have two slits that have a very narrow opening about the wavelength of the light, and they have a distance between them. And what we're going to do is we're going to draw that first line, the distance straight across from the center of the two slits to the screen, and lining up with all of those crests right in the middle where the crests all line up. And what we're going to do is we're going to draw that line and label it L. And this is the distance between the slits and the screen. Now, Y on the screen is the first order magnitude. That's the first bright spot beyond the 0 order magnitude straight across from the slits. So we're going to draw the line from the center of the slits all the way to Y, and we're going to call that L prime. And that also lines up with all the crests as well. Then we're going to complete the triangle, and the distance between the 0th order magnitude and first order magnitude bright spots, we'll call that distance Y. Now, we're going to draw the path that light takes from each of the slits. So from the dashed lines represent the distance that light travels, the path that it takes from slit 1 and slit 2. And what we're going to do is we're going to draw a line from the center of the slit 1 that's perpendicular to L prime and ends at S2. Then we're going to draw a horizontal line from the middle of S1 to S2. We're going to call that D, lowercase d, and then we'll complete the triangle and we'll call that delta capital D. Lowercase d stands for the separation between the two, and capital delta D we'll talk about in a second what that represents. Now, these two triangles that we drew, we can see that these two triangles are actually similar triangles. So if we label an angle theta between L prime and L, we have that same angle on our smaller green triangle that's going to be between D and the unlabeled leg. So what we know is we can solve for delta D, and that's just going to equal the opposite side, which is going to be our hypotenuse, times the sine of our angle. And that theta bright means that's a bright spot, or the first order magnitude that is reached from the point Y that's labeled on the screen. So what does delta D represent? So if we draw the path that light takes from S1, what we're going to do is we're going to count the number of wavelengths it takes for S1 to get to Y. So we can see that takes 1, 2, 3, 4, 5, 6, 7 wavelengths to get from S1 into point Y. If we do the same for S2, 1, 2, 3, 4, 5, 6, 7, 8, it takes 8 wavelengths to get there. So the path length difference is what delta D is called, and delta D is the wavelength of the light because it takes 1 extra wavelength to get from S2 to Y than it does S1 to Y. So that's called the path length difference. And the path length difference is just the wavelength of light. Now, if delta D is equal to the wavelength of light for the first order magnitude, what does the delta D represent for the second order magnitude? So let's draw the triangle, and we have L double prime, and then we draw the distance on the screen between those two is Y. So we're going to draw that line that goes from the middle of S1 perpendicular to L double prime, and I didn't put the arcs on there or the path, but that's where it ends is at S2. And then we draw delta D, and what we would find if we had all of the arcs for the wave of light, we would see that S2 travels 2 extra wavelengths to get to 2y than S1 does, so delta D is equal to 2 times the wavelength. Now, if we repeated this process for the third and fourth, we find that it would just be 3 wavelengths, 4 wavelengths, so on and so forth. So we can rewrite this as delta D is equal to some integer that we'll call a lowercase m times the wavelength. Now, delta D is the path length difference, or the extra number of wavelengths traveled to the bright fringe measured in meters. M, as we mentioned before, is the order of the bright fringe. That's an integer, so 0, plus or minus 1, plus or minus 2, etc. Each number represents the 0th order magnitude, first order magnitude, second order. Positive would be to the left, negative would be to the right on the screen. Then we'd multiply m times the wavelength of light measured in meters. Then delta D is also equal to the distance or separation of the slits measured in meters. And then we multiply by sine of theta bright, and theta bright is just the angle between the screen distance and the straight line distance to whatever order magnitude we're measuring to, the first, second, third, etc. Now, delta D equaling two of the same things means that obviously those two are equal, so m times lambda equals d sine theta bright, and again, m is just that integer 0, plus or minus 1, plus or minus 2, etc. Now, that explains the bright spots, but let's explain how we can find the length of on the screen to the dark spots. So we can see that a crest and a trough are lining up. That's where we have our dark spots on the screen. So when we have a crest and a trough, we know that it's not the same distance. So we're going to label the angle between the 0th order magnitude and the first dark spot as theta dark. So we look at our equation, m lambda equals d sine theta bright. That's how we find the first, second, third order magnitude for the bright spots. But the dark spots are not the same number of wavelengths. It's only a half wavelength. So we take d sine theta dark and we multiply the wavelength times m plus a half. So we can plug in 0, plus or minus 1, plus or minus 2 to find the different order magnitudes for the dark spots on the screen. And that's what the 1/2 takes care of, is that it only travels a half wavelength difference in the path to the screen. Now, if we have a small angle, we can use what's called the small angle approximation. And this applies for angles of theta when theta is less than 10 degrees. So what does this mean? Well, if we look at a ratio of y to L on our triangle, we know that that's opposite over adjacent, which is equal to the tangent of our angle. So y divided by L is equal to tangent of theta. But we also know that tangent of theta from trigonometry is sine theta divided by cosine theta. Now, when theta is less than 10 degrees, that tells us that we calculate that value, cosine is approximately equal to 1. So that means we'd be dividing by 1, which gives us that tangent of theta is approximately equal to sine of theta, which means that y over L is approximately equal to sine of theta as well. So if we look at our equation, instead of writing sine theta bright, we can substitute in y over L. Y max just means that it's a bright spot, so m lambda is approximately d times y max divided by L. Now we're going to transition and talk about diffraction grating. So what a diffraction grating is, instead of just having 2 slits like Young's double slit experiment, we have hundreds or thousands of slits per millimeter, and usually it's on a piece of glass, or lines is what you'll also hear called lines or grooves. What this does, it creates a sharper, more well-defined interference pattern, so you can see it a little bit easier because you have more constructive interference going on because you have more waves being diffracted from the slits. And this is much more accurate than using a prism to separate white light into its spectrum Now, diffraction gratings, if we look at our equation, a common diffraction grating, let's say we have a 500 lines or grooves per millimeter. Now, what this helps us find in our equation is the distance d, the separation between the slits, and that's the inverse of the diffraction grating. So to calculate the separation between the slits, we just do 1 divided by the diffraction grating. Now this gives us an answer in millimeters, but we need d to be in meters, so you multiply that by 10 to the negative third as well. So 1 divided by 500 times 10 to the negative third, that's going to give us 2.0 times 10 to the negative 6 meters, and this is the separation between the slits. That is the d value that we have in m lambda equals d sine theta bright. We're going to transition to single-slit diffraction. So single-slit diffraction works much like double-slit diffraction. Now we have a very thin opening, so we'll label that A. That's the opening length. A is a very small opening comparable to the wavelength of light used. So what we're going to do is we're going to shine a laser beam on that very small opening, and those red arrows represent the beam. And then it would be very complicated drawing if we drew all of the waves interacting with each other. So we're just going to draw one path that light would take as it diffracts. Now we're going to separate the opening into top and bottom. So we're going to cut it in half. And so we know the length's going to be A over 2. And we can make the same drawing we did on the double slit where this time we have 2 triangles. And those triangles are both congruent triangles. And if we draw the normal line to the center of the opening and we label the angle theta, we know that we have similar triangles with those small triangles, much like we did in Young's double slit experiment, which means this length of the base of that triangle is going to just be the hypotenuse times sine of that angle since it's the opposite side. So all of our waves are in phase as they reach the slit and move towards the screen. The waves will converge a long distance away. So what this means is that opening is about, say, 700 nanometers, about the wavelength of red light. A long distance away would be 1 meter. Now, the path length difference for corresponding waves from the top to the bottom, because they're mostly in phase, they get out of phase by half of a wavelength by the time they get to the screen. So they're out of phase by a half a wavelength. So that means if they're out of phase by half a wavelength, what we're going to end up with is the crest lining up with troughs, which means it's going to cancel out. So we're going to end up with dark spots on the screen for that point, and that causes destructive interference on our screen. If we know that A over 2 sine theta dark is equal to a wavelength divided by 2, we can rearrange this, and A sine theta dark equals the wavelength. And we know that wavelength is the path length difference, so delta D equals m lambda. And we can substitute that in where m lambda equals A sine theta dark, where m is that integer, and that helps us find the first dark order, the second order for just single slits. So if we look at a drawing to the screen, so we have the normal line from the center, we'll call that L. We can see the intensity of light, where in the center we end up with a very large amplitude. We'll draw a dashed line to the first order minimum, and the second order minimums, you can see where the transverse pulse is showing a cancellation where destructive interference would go. And what you'd see on the screen is very bright spot in the middle, and then you'd see some bright spots, but they wouldn't be as bright as you'd see in a double slit experiment. So m lambda equals A sine theta dark, and that theta dark is to the y min 1. And what we can do is we can use from y min 1 over L, we know that we can use a small angle approximation. So m lambda is approximately equal to A, which is the separation between the slit, and that's y min divided by L. So let's recap single and double slit equations. So both of them use delta D equals m lambda, where m is that positive integer. Delta D equals A sine theta dark, where A is just the opening of the single slit, whereas in double slit equation, delta D equals D sine theta bright, where lowercase d is the separation between the center of these slits. And using the small angle approximation, we can substitute for A sine theta dark, y min divided by L, And for double slit, we can substitute Y max divided by L for sine theta bright. Now, the double slit equation, we can also find the places where we have destructive interference by using the equation of m plus 1/2, that quantity times lambda, equals d sine theta dark, and that helps us find the location on the screen from the 0th order of magnitude to the first dark spot or second using an m value. Now, we talked about electromagnetic waves, and we've been talking about light, visible light, but radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays are also forms of electromagnetic waves. All of them travel at the speed of light, which is 3 times 10 to the 8th meters per second, and what causes them is an oscillating electric and magnetic fields. Now, the changing electric field induces a changing magnetic field, and vice versa. So when we learned about magnetism, we learned that a moving charge produces a magnetic field, and a magnetic field has an impact on moving charge. So what's happening is that the fields are causing each other, as one decreases, the other decreases, and one increases, the other increases. So they're causing each other to increase and decrease, and that's what's causing the oscillation in our electromagnetic wave. Now, the cycle continues as the wave propagates, and this is why it doesn't need a medium. So if we look at the electromagnetic spectrum, you can see in between 10 to the negative 7th and 10 to the negative 6th wavelength, that's where our visible light spectrum is. So 400 nanometers is our violet end, and 700 nanometers is the red end. And we can see on the left side, we have short wavelengths and high frequencies, where we've got gamma rays, X-rays, and ultraviolet radiation. And all of those have very high energy. So the further left, the higher the energy, the smaller the wavelength. So gamma rays having a very small wavelength means that they can go through things that have very small openings. So like it can get through your body and it can interfere with the structure of the cell, which causes mutations, which is what causes cancer from gamma radiation, which is something that happens in nuclear reactions. Now, on the right side of the electromagnetic spectrum, we have long wavelengths, low frequency, and low energy, infrared rays, microwaves, and radio waves. Microwaves are radar, microwave ovens. You also have some FM radio stations. The radio waves are the AM radio stations, the television stations. Bluetooth is also used radio waves, as well as Wi-Fi uses radio waves as well. Now, an electromagnetic wave travels, and the way we determine the direction is using a right-hand rule. So if you're given a still picture with red representing the electric field and blue representing the magnetic field, you'd use your right-hand rule using your index finger, thumb, and your middle finger, and you'd orient it like this. Now, the electric field is your index finger, which points up. Your middle finger would represent the magnetic field, which points to the left, and your thumb would represent the direction of propagation of that wave. So you'd show that it's moving to the right. And if we set that in motion, you can see that the electromagnetic wave is moving to the right. So this is an introduction to electromagnetic waves. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X @CaviCoaches.